I'm going to introduce our first speaker, Mohit Lad. He's a co-founder and CEO of Thousand Eyes. He received a PhD. Why are these going? Received a PhD from computer science from UCLA, where he conducted research in the area of large-scale network diagnostics. Prior to Thousand Eyes, Mohit contributed to the Traffic Explorer product at Packet Design, and later worked at Nokia, where he built systems to monitor mobile service performance. Mohit is an active member of CHI-NOG and is currently serving at it.
That is an older guy. I'm not on the program committee anymore.
Okay. Well, thank you for your contributions to it then.
Be on the program committee.
Yes.
Right, there you go.
He came in all the way from San Francisco just for us, so please give him a warm welcome.
All right. The first, can you hear me? Can you hear me in the back? The first thing I need to check is to make sure all the chats are off, so we don't get embarrassing messages during the presentation. So as Tom mentioned, Mohit Lad, I'm the CEO of Thousand Eyes. We're a tech startup doing a lot of stuff in the network space on troubleshooting and active monitoring and so on. But this talk is really not about the company. This is more about the philosophy of what we can do and as people doing network troubleshooting. And as Tom mentioned, a quick background on myself. I did a PhD at UCLA for God knows what, 5 or 6 years, which basically means that when things break, and you guys as network operators have 5 minutes to fix it, I get about 5 years or 6 years, and I can spend about 1 year thinking about how to fix it. I can spend another 2 years trying to devise a scheme and another 2 years writing about it. So that's the key difference. But excited to be here, and I'd been giving a lot of thought to what I really wanted to talk about here. And essentially the crux of what I want to convey here is there's this world of passive monitoring and there's a world of active monitoring. And in an ideal situation, you want to combine both. And I wanted to get more theoretical on this. Then I realized that you guys are going to probably fall asleep. So what I've done instead is I've tried to get together a set of events that I think are really interesting that have happened in the internet in the last few months or recently. And those events will give you guys something to think about on what really happens out there and how we can potentially learn more about things. So just quick basics on what we mean by passive monitoring and what we mean by active probing. Since I was making my slides on the flight, I just captured what the definition of passive monitoring was on Wikipedia page. And it says capture traffic from network by generating a copy of the traffic. That's passive monitoring. And we all know when we look at TCP dump, we look at Wireshark, whatever you guys use, you're constantly looking at stuff that is flowing on the wire. And it's really useful when it comes to the first step in understanding what's going on. But typically, it's very hard to explain the reason behind the behavior. You can spot the behavior, and in some cases you can explain the reason, but in a lot of cases, it's really showing you what's happening from an end-to-end standpoint, and it gets really hard to figure out what's going on in between. In contrast, active monitoring essentially means you're generating synthetic traffic to probe something, to discover something. By the way, I want this talk to be interactive, so feel free to stop me, raise hands, or just abruptly interrupt me anyways. It's a knock crowd, so we're not polite here. It's okay. The typical examples are the pings and trace routes and so on. And the idea is when you see a problem, you start doing a trace route. You're not sitting at your terminal and doing a trace route every 2 minutes, right? So it's usually very reactive. It's very much driven towards finding root causes. All right, so we'll start with an example, and I'll go through the steps here. So the basic problem here is you have a client trying to load Google, doesn't work. Somebody calls in and says Google's not loading, right? So this is their view of the world when they're calling and complaining. There's a client, there's a server, and it should just work. It's really simple. But if you break it down, the first thing that's happening here is you're trying to resolve google.com. So you obviously have a local resolver, a local caching resolver that you're going to, which is either if you're in your enterprise, it's your enterprise resolver. If you're at home, it's probably your Comcast or Cablevision or so on resolver. And you ask google.com to that resolver. If they don't have it, they will reach the .com and do the whole DNS trace. So we all know how this works. Does everybody know how DNS works? All right, that's good. What I'm trying to get at here is let's just focus on DNS troubleshooting, right? So in an ideal world, you query for Google and you get a reply. Now the first thing you do when you're looking at TCP dump is you're looking at the DNS traffic and you're looking to see if you're even getting a reply back from the end user, right? So if you don't get a reply, if you get a reply, then you can probably assume that DNS is working okay. But if you don't see a reply, then what can TCP dump tell you? Probably not much beyond that you're not getting a DNS reply. So next step really is to figure out how do we go from there to figure out what part of the DNS chain is failing, right? And that gets pretty interesting. So the first thing you would check normally is just make sure your local resolver can resolve other domains. Otherwise, it's just completely toast and you don't have to do any more troubleshooting. Or you can change your resolver to a Google DNS or so on. So that's a basic step. We all do that. But if that also returns okay, then the rest of the things get really interesting. So now you're trying to understand what part of the DNS chain is breaking, and you actually have no visibility into it unless you generate some set of probes, right? So this gets really interesting. So in order to understand, we'll use a real example. So this is a real domain from October 9th, which was it yesterday or today? Kind of lost track of time here. Been flying a lot. So it's today from an hour ago or a few hours ago. And what you notice here is Buenos Aires from Argentina cannot reach a particular domain. And I've blacked it out because I didn't want to shame anybody here. But we can't, that particular site cannot reach a domain, so the DNS resolution is failing. And it's similar to this simple example I gave you before, right? So we want to try to troubleshoot it. So the first thing we try to do is find out what the name servers are for that domain and whether I can reach the name servers. But when I try to dig deeper, what I realize is this particular domain is actually anycasted. So when I look at the name server and I run a trace to the name server, now this is where active probing becomes really important, right? So if you just do a DNS query, you probably get a response, you don't get a response. You're not really sure what's going on. So the next thing you try to do is you try to trace the actual path that is being taken at the network layer to the DNS server. And I'll get into a little more details about traceroute and what's really hard and easy about it, right? But this map shows the path traces from various locations to that particular name server. And the first thing I will highlight here is looking at this map. Based on my experience, I'll say this is an anycasted domain. And the reason I say it's an anycasted domain is because you will see that at the server, maybe I'll use a mouse pointer. So the server has various next hops, which is very, very uncommon. Usually you would have a 2 or 3 next hops. And so this has a host of next hops right here. So that's one sign. But the other sign is if you just mouse over on some of, if you just try to understand the latencies from each location, right? So you'll see that this particular server is 10 milliseconds from Paris, and it's 55 milliseconds from Sao Paulo. Now we all know if we put a compass in the center of Paris and draw a circle around 10 milliseconds and where we can reach, and we go to Sao Paulo and draw another circle, it's going to be a big disconnect there. So that means that this particular IP is being announced out of multiple locations, right? How many people here have worked with Anycast directly? All right. How many people think it's fun to work with Anycast? All right, life gets interesting. So as we know, Anycast troubleshooting can be really, really frustrating. So what we do next is we try to now understand what instance is the query from Sao Paulo going to, right? And the way you can typically figure this out is what the next hop is, because really if you just look at response, unless you have encoded something in the name server which responds to a TXT record in a unique way, and there are these things, they are not very well known, but you can always find these out. So even for things like the root servers, you'll find sometimes that you can just do TXT queries and find the actual instances, but it's not always obvious. So if you don't know that, the only other way you can find out what the instance is if you look at the next hop. So when we look at the next hop here, it's in Brazil Telecom. And what we realize is Brazil Telecom is having some serious packet loss issues, and the Anycast instance that is operating out of Brazil Telecom is actually having some problems. And so if you were to actually reach another Anycast instance, you would have been okay. But because you're local and you're trying to get the best possible route, which is the shortest route here, you're actually in problem. And this is a situation where if you weren't Anycasting, or if you had something where you had GSLB, you probably would have been okay. Does this make sense? It's just a very simple DNS troubleshooting example, right? So just to help you guys understand, it's important to look at all these layers together. Now let's assume that if DNS comes through and we get a reply, I said earlier that yes, everything is okay, and the question is everything okay? So in order to examine that, what we'll do is look at what Facebook.com resolves to from everywhere across the world, right? So we've collected data from I think over 1,000, maybe 1,600 points here, and we're trying to find out what Facebook.com is resolving to. And we're looking at the NS record. Now the color coding shows you the availability of Facebook in different regions, and what is interesting is in China, only 10% of China can resolve the Facebook NS record. The remaining percentage of China, or networks in China, are actually just getting no mapping, which is an MTA record for the NS record, right? So 10% of China can potentially reach Facebook if you look at this, because NS records are being available for 10% of China. In order to verify that, what we do is we try to look at the Facebook A record and see what happens there. Now if we look at the Facebook A record, we see that 100% of China is getting an A record. So now that's interesting. They're blocking about 90% of traffic on the NS records and returning empty answers. And for A records, you're getting a complete 100% result. So interesting, but now let's try to look at what the result is. So when we look into the actual IP addresses that are thrown for Facebook, we find that about 95% of the world is going to this particular IP 173.252.126. And so if we do a quick check, that IP belongs to Facebook. It's a block, it's a /20, a /18 that is announced by Facebook. So that's all good. But we notice that only 1% of China is actually seeing that IP, right? So that's interesting. What does China actually see? So if you look at China, they have a bunch of IPs, but 72% of China sees this IP 37.61.54.158. Any guesses on what this IP is? You guys want to take a shot at where this block is being originated from?
The Great Wall, right? The Great Wall.
All right, so that's what I thought, but what I did was I tried to do a lookup on this block. And here's what's happening here. We all know this, but essentially they're throwing out a fake IP, and they're blocking they're intercepting the queries and throwing out a fake IP, and it's a common way to do intercept traffic. If I do a query, this block is being announced out of Azerbaijan, out of a company called Bak Telecom, which is just really, really bizarre. It's just, it's very bizarre that I'm seeing the Chinese government actually put in an IP in a block that is being announced from Azerbaijan. So very interesting observation that completely surprised us, and I thought it would be interesting for you guys to just take a look at it as well. I don't know actually what they're trying to do. I can't predict. Yeah, so they're blackhauling traffic, right, essentially. And even if you actually, I mean, DNS is just one of the ways. They use TCP resets, they delay packets, they put holes in segments. I mean, they do all kinds of stuff. And if you guys are interested in how the firewall operates, I have a really nice paper that actually has done a great study on this. Another PhD student who spent 5 years studying this. So, but it is possible. I haven't checked on that. Yeah. The one thing you could do now, if you were Facebook and you were really serious about getting China to access Facebook and get around this trick, does anybody know what we could potentially do?
Get M6 to open up an internet exchange.
That would be good, but you could potentially hijack the prefix and announce it, and as Facebook could potentially just hijack the block accidentally, or buy it, yeah. Yeah, the VPN services are obviously a way people try to get around that as well, yeah. Yeah, so based on all these examples I'm giving, I'm going to be really careful traveling to China now, but hopefully these things are never broadcasted. All right, so we'll talk a little bit about traceroute because I showed some part traces, and I want to go into some details here. So we've all used traceroute, I'm guessing. Now traceroute, the results really vary depending on what protocols you use and how you use it, right? So by default, if I remember right, traceroute uses UDP, and then you could use ICMP or you could use TCP. And one of the main challenges with traceroute is people tend to use ICMP, which has its own sets of issues, because we found actually that ICMP traffic can take a different route than the TCP flows that are going through. So you're potentially troubleshooting a path which is not actually on the application path that you're having problems with, right? The other thing we find is ICMP is blocked or throttled or so on. And I swear to God, this is a really interesting story where at one of the NANOG, this was about 5 years ago, there was one of the NANOGs I was having a chat with a small network operations, small ISP's network operator, and he was a little bit buzzed, and he told me that he has set up rules where any ICMP traffic is taking the best path. So he was almost like reverse routing, where he was almost reverse optimizing where ICMP was taking the best path, because he knows that the customers send ICMP to figure out like what's going on. So I hadn't heard that one before, but that was pretty interesting to me. So the rule of thumb I would say for people is, when you use something like traceroute and you're troubleshooting an application, figure out what protocol the application is using. If you're troubleshooting voice, you want to do UDP troubleshooting, right? And if you're troubleshooting web or any other applications, you want to do TCP-based troubleshooting. And the other thing with traceroute is you always want to find a way for the traceroute to hit the actual final destination. Otherwise, you won't differentiate from basic probes being blocked and being able to reach the final destination. So these are stuff I can go into details during the happy hour and during the social or so on. The other aspect of traceroute which can get really interesting is load balancing. And do people know the concept of parish traceroute? How many people know the concept of parish traceroute? All right. So the basic problem with traceroute, if you have load balancers, is you can have one probe go this way, the other probe go this way. And I could draw on the whiteboard to just have is anybody interested in a problem here? So do people want me to draw something on the whiteboard? All right, I'll do something real quick here. Do we have a marker?
I've got markers.
Are you prepared? Permanent markers.
Not whiteboard markers. Pick your color.
I'll just do one here. So this is a
How do you
simple.
tell the sales engineers from the guys who actually work for a living?
All right, so let's assume this is the topology that we're trying to understand, right? And you send a traceroute. So when you have a TTL1, you're getting a response from B. So your inference is there is a path A to B. Now you send a packet with TTL2, and the packet, because this is a load balancer, it goes this way. So you infer there is a link C. The third packet with TTL3 goes this way, and it ends up at this hop, right? So you will see a response from E, and so you're inferring this link CE, which does not exist, but I've also missed out the hop D. So that's really the issue with load balancing. And parish traceroute is a notion of using the same. Sorry. Oh, I'm sorry. There you go. So the notion of when you're just using a traditional traceroute, you're going to go through these problems if you're going through load balancers. And so the idea of parish traceroute is to use the same 5 tuples, so you can actually send traffic through the same load balancing flow. And it only works if you're doing per flow load balancing. If you do per packet load balancing, then it doesn't really work, but it still helps. There are a few other issues here which really include differentiating from muted losses and figuring out if you have multiple routes, you need to actually send several probes to discover everything in the environment. But traceroute is, we actually have a blog that one of my colleagues wrote on just cribbing about traceroute. So it's a really nice blog, and I'll point you guys to that, or you can just go to blog.thousandeyes and search for traceroute. So now getting into like examples just to show some interesting stuff. And we're all, people are network operators here, so you relate to some of this stuff. Sometimes you're fixing things late at night and you make some mistakes. And so I'm going to try to show some interesting stuff. Is anybody here from Country Financial? Before we go about embarrassing them? All right. So what you see on this screen is a simple availability graph showing the availability of the site, Country Financial, and this is like during the day. It's 1700 UTC, which is pretty much in the middle of the day, right? And there's a lot of availability dips there. Now, if you go from the application layer to the network layer, what you'll notice is a spike in packet loss. That timeline there is showing packet loss. So there's a lot of packet loss, and all these circled nodes are where packets are being dropped. They're kind of all over the place. They're in different ISPs and so on. So it's something bizarre going on here in the network where different ISPs are dropping packets. And when you usually see loss at different ISPs in a forwarding path, there's a very strong indication of a BGP problem, because otherwise it's really unlikely for forwarding for nodes to drop packets randomly at forwarding layer unless there's a control plane issue. So just looking at this, I can say that it's very likely to be a BGP issue. So what we'll do is we'll look at BGP. But before that, you can notice here there's loss in quotient, there's loss in access, CC, so there's a bunch of nodes. Now, if I look at the BGP connectivity, this particular node here is Country Financial's AS. They are upstreaming through one. I actually don't know what 40948 is. I know the common ones, but this is an unknown to me. But they have a single upstream there who uses 6939 is Hurricane people, HE, and 174 is Quotient. Yeah. So two upstreams from there, and these set of green nodes are not seeing any BGP changes, but that set of red nodes are seeing a lot of BGP changes. So one of the upstreams is really having BGP flaps, and that's causing potential control plane issues. And this coincides with a much longer period where you actually have these issues going on and on and on. Now, clearly somebody was trying to do something. Either they were trying to fix something or they were trying to change something. What we noticed is after things get stable, we'll notice something interesting. Now I'm going to actually throw this up there and ask somebody to tell me what happened here. This is after things were stable.
Looks like one of the upstreams got turned off.
No, so the hops have been basically reduced. So what it shows there is not the entire picture. It still has more hops, but you're right. There is, 209 instead of this long. What was that? 40948, right? But something else has happened there. There's another hop on the left there, which is AS 15011. Notice how the digits of AS 15011 and 10511 are the same. And this is what happens when AS prepending is not done with the same actual AS number. And so somebody who was trying to troubleshoot this decided after all this that, okay, I need to use prepending to make this route more lucrative, and they decided to add the AS number twice, except they skipped one digit in here and there. And so now you have a BGP path that actually starts with 10511, goes to 15011, comes back to 10511, and then goes back. So the 3-hop connection. So, and this has been going on for a long time. So, and we didn't tell them because it makes us look look good because we're finding interesting stuff. So, so this was another fun event. DDoS, always fun. Lots of activity going on. So this is a DDoS attack on HSBC, us.hsbc.com, and usually we see a lot of interesting network behavior during DDoS attacks. But in this one, what we notice is that there's a small dip, and then things are pretty stable. Like things are at 100%. So maybe it's a small DDoS attack that they managed to handle right away, or maybe it's an attack that was just handled better. So we'll find out. What you'll notice as you go to the network view is during the time where the availability was low, it has HSBC was using two upstreams, AT&T and Verizon, and both were dropping packets. They were just hammered, and in both the upstream, the edge routers were dropping packets essentially. But what happened was, it was really interesting. What we saw was, when we look at the BGP and we step through, what we'll notice is suddenly there's a new autonomous system that crops up, which is this guy here, and that belongs to VeriSign. And this was the old autonomous system from HSBC, and the red link is essentially saying that origin is completely gone. So VeriSign has started announcing that same block as part of VeriSign's infrastructure in order to mitigate the attack, and VeriSign has DDoS mitigation. VeriSign, Prolexic, Akamai, they all do cloud-based DDoS mitigation, and essentially there are two techniques primarily. You either do BGP or you use DNS, one of the two, right? So in this case, this was a BGP-based DDoS mitigation handling by VeriSign. Whatever they did a good job because the availability was okay, so nothing crazy happened. Any questions on this one? So I have one last example, and is this useful? All right, good. You people are nice. So one last example, and I've tried to pick like different breeds of examples just to show interesting stuff. So here's a case where we have PayPal, and PayPal was having some availability issues from one location, and when we tried to use all the network probing techniques that I said, like these things, all those things, and we try to trace the things, we find out that there are some hops where packets are being dropped. And again, we saw a little bit of a behavior where it wasn't just one ISP, it were like 2 or 3 different ISPs where there were packet drops, which suggested that there's something related to BGP that is going on in this space. And coming back to what I just realized, my talk was titled Combining Active and Passive Monitoring. And one of the things that I consider as passive monitoring is listening to BGP feeds, because essentially you're not generating any traffic, you're just listening to something. So if you're collecting BGP data from multiple locations and you're just looking at it, that's passive monitoring to me. But in this case, we suspect something's wrong with BGP. So we look into BGP. And what we notice is Akamai is actually announcing the block, that one of the blocks, and Akamai is announcing multiple blocks, but one of the blocks that Akamai is announcing for HSBC, it's right here. So this is 16225 is Akamai. That's the origin AS. But on the corner there, which I'll highlight in the next slide, you have another AS number, 4761, which is Indosat. And Indosat apparently leaked a bunch of blocks. This was not very long ago, so you guys might have read this in CHI-NOG forums or outages lists and so on, but I think it was like 3 months ago or something, potentially 3 or 4 months ago. So this is Indosat actually announcing a bunch of blocks, and the way BGP works, not everything affects everything, but they did actually impact some US sites just because of the way the AS connectivity was, and ended up with taking things like PayPal out for some locations. So at a high level, all these things really shows you that troubleshooting can be pretty complex, and it can involve not just understanding the application layer stuff, but understanding all the aspects of the infrastructure, DNS, understanding the forwarding layers, understanding the control plane. And not many people really outside of the operations group understand how hard these things are. So like Tom said, if things don't break, people don't appreciate what network operations does, and only when things break and things are fixed, people start to realize that. So that was my last slide. Really want to thank you guys for having me here. This has been great. You guys are a great audience, and I will make sure the next time I come to Chicago, I'll dress up a little better. I didn't realize that people are pretty well dressed here. But thanks, guys. Any questions? So you can find me if you have any questions or want to chat about stuff. Thanks.